Hello fellow robotics enthusiasts. In this lecture we would be studying a fundamental search algorithm called Uniform Cost Search or UCS. It forms a base for the A-star search algorithm which we would cover next week. Suppose you have a robot and it has to reach a goal. There are a number of ways for it to reach the goal. In UCS, the robot chooses the path that has the lowest path cost. Let me explain this statement. Now the path cost can have different meanings. It can mean the distance traveled, it can mean the velocity, it can mean acceleration, or it can also mean the fuel consumed. It's up to the robotics engineer to decide that. Let's suppose it means distance traveled in an example. Now the robot can choose multiple paths to reach the goal. It can take this path, it can take this path, and there could also be another path that I have not yet described here. Just remember that UCS chooses the path with lowest path cost, and you can solve any problem related to it. UCS algorithm guarantees optimality. Let me clear the screen and explain further. So let's assume you have two Python lists. One is called visited and one is called frontier. Right. Now let me explain the propagation, how the robot will decide its next node to visit. So let's say there's a robot, right, that I've drawn. So first, it has two options, right? It can choose A or it can go to B. Now, A and B are not the goal, right? So the robot knows that after visiting A and B, it has to continue its search. So it can't stop the search. So these two nodes, A and B, will be added to the frontier. So frontier now contains A and B. Alright. Now A has a cost of 8, and as I told you, cost can be in terms of path cost, like distance traveled, velocity, fuel consumption, anything. It's your choice. So let's say the path cost here, let's assume we are dealing in terms of distance to make it a little user friendly and easier to understand. Let's suppose A has a path cost 8 and B has a path cost 7, and it is added to the frontier, which is a Python list. I would also be walking you through the code of the UCS in the later stages of the video, so hang on. Now, out of A and B, which has the lowest cost? B has the lowest cost, that is 7, because so typically we use a priority queue in doing the sorting automatically, but now you can also assume that we have sorted the list, and after sorting we get B7, A8. So the robot chooses B for expansion. So now let's assume the robot chooses B for expansion. So when it chooses B for expansion, B is as added, B's children are added to the frontier. So now the frontier will have A8 and B's children, that is D. Now the important thing is the cost of D would be the distance the robot has to travel to reach D, and that is here 7 plus 1 is equal to 8. Now D has 8 cost, right? And since B has been fully explored, so we have fully explored in AI terms mean that we have added its children to the frontier. So B has been fully explored, so we add it to the visited list. So we add B to the visited list, right? So now, as you can see, the path cost is same. It is 8 and 8. Now it's the responsibility of the robotics engineer to decide how to break the tie. So now I've decided to break the tie alphabetically. So I decide to expand A. So when I expand A, I get its child, that is C. Alright. So I add C to the frontier, and it has a total cost of 17. C has 17 and D has 8. Alright. And before expanding A, I also check if it is the goal or not. So right now A is not the goal, so I expand it. I get C, and I put A in the visited list. Right. Now again I sort those elements and I get D to have the lowest cost. So this has the lowest cost right now. So I check if it's goal or not. So clearly it's not the goal. So I add its children to the frontier. So now So now the frontier will have C17, and the child of D is the goal itself, and it has a cost of 7 plus 1 plus 4, that is 12. So goal has a cost of 12, right? And since D is not the goal, I check it and I add it to visited list. So now the visited list contains B, A, D, right? So now I again begin with frontier and I see which node has the lowest cost. So now the goal node has the lowest cost of 12, and I check that is this node the goal, and the answer is yes, it is the goal. And since it is the goal, I declare that I have already reached the goal and there's no need for expansion. So now the optimal path is this is the optimal path for the robot to take. And as you can see that UCS guarantees optimality, and this is always the case. UCS is an algorithm that selects a node n for expansion. The optimal path to that node has already been found. Another important thing that to keep in mind is that the goal test is applied to a node when it is selected for expansion. Normal algorithms don't work that way. So that is one special way for expanding the node in UCS. Second thing is that so I hope you are able to understand UCS clearly, and I would also like to explain the path propagation for UCS to give you a more intuitive feel for it. So let's suppose you had a robot here and your goal was to here, right? Let G be represented as a goal. So the intuitive way to understand is that the robot, it searches for the goal in concentric circles. So first it searches for goal at a circle of 1 meter, then 2 meter, and so on. Let it be n meter till it reaches the goal. A star is different from this, and we will see it next time, but this is a very important concept to keep in mind, that it searches for the goal in concentric circles, and these are perfectly concentric, right? These are not ellipses, these are circles. So this is something extremely important and extremely conceptual to keep in mind. So I've just opened this Python shell and I'll be walking you through the code of UCS. So as you can see here, I have given an input as a problem. So problem can be anything, right? It can be the real-time coordinates of the robot and the goal. It can be a predefined static map of the goal and the robot. So it can be anything. So as again, I have defined frontier to be priority queue. So in the video, as I described, I always sorted the list. So now I don't need to sort the list. I have only used priority queue and it works on its own and is more efficient. And I've used visited to be set rather than normal list, and it is set of list. The reason is that I want all my nodes to have unique values, right? I don't want any nodes to be repeated to have duplicate values. That's why I've used this. And I just normally start with a start node, that is the starting position of the robot, and if that starting position is already at the goal state, I return already in goal, right? Else I push it to the frontier with the priority, and so I also push the path to the frontier, because then it's easier to return the path when the goal has been reached. So let me tell you what I'm talking about. So it just says that in this line it just says that while frontier is not empty, and it's like a short way to describe it in Python. So while frontier is not empty, I pop the elements from the frontier and I store it in variables current, that stands for current node, and the path, that means the path till that node from the starting node. And then I just check if that current node is already in the goal state, and if it is, then I just return the path. So that's why storing path is a useful option in the frontier, because when the goal is reached, for example, the current node is the goal node, so I just return the path, and that path is the path that the agent has already traversed to reach the goal. So I have stored the path. That is one useful reason to store the path. So if its current node is not the goal state, so then I store its children, that is from the get successors function, I store its children in the variable next, right? And so next contains all its children, and for states in next, that means for all the children in the next variables, I then add them to the frontier, and then that keeps on going until and unless I reach the goal. And if I don't reach the goal, then the algorithm will just keep on running until every node has been explored. So this is one of the way to code the algorithm, and it is not the only way. There are many other ways, and there are many other simpler ways. This is not the most efficient, but this is one of the ways. Again, I'll be posting the code in the description so you guys can look at it, and do let me know how this video was for you guys, if something that I can improve. And please subscribe to this channel. This is a channel that I've just started to make the robotics knowledge open source and to share with more number of students that I can. And so if this video comes out to be helpful, please give it a like and please subscribe. Thank you so much.